This video focuses on Big Idea 2, which is about chemical bonding and phases. This is just part 1 of Big Idea 2. Part 2 will follow in another video. So first thing, atoms get together to form bonds. This is what gives us the diversity and myriad of different compounds in the universe. Some of those atoms, when they get together, form things called ionic bonds. What do we know about ionic bonds? Electrons are transferred, which gives us charged molecules. So, NaCl is formed with an Na positive, Cl negative, opposite charges attract, that forms the bond. This leads to the properties you need to know, high melting points and boiling points, and ionic compounds tend to be pretty hard. Other compounds that could be ionic, MgCl2. How does this split up? We form Mg with a +2 charge because it's in group 2, and 2 chlorines with a -1. These are opposite charges. Which of these would have a stronger bond? Well, we need to be able to predict that qualitatively. Magnesium 2+ has greater charge than Na+. So since it has greater charge, this would be a stronger bond, so you would expect it to have, a higher boiling point, higher melting point, boiling point, etc. If you have two molecules with the same charge, like NaCl and NaF, for example, then the atom that is smaller is going to have a greater charge. And the reason for that is because a smaller atom means closer together, Coulomb's law. So since fluorine is a smaller atom than chlorine, this would be a stronger bond, higher melting point, higher boiling point, because fluorine has a smaller atomic radius, and due to Coulomb's law, when charges are closer, there's more attraction between them. Oh, sorry, for ionic bonds, always between a metal and a nonmetal. What about metallic bonds? Metallic bonds form with metals, and what's special about them? They have what's called a sea of delocalized electrons. What do we mean by delocalized? Delocalized basically just means free, as shown in this diagram. So these are all metal ions with these positive charges, and the red circles are the electrons. And these electrons can move freely over all of these atoms. They're not stuck to one particular atom. And since these electrons can flow so freely, the metallic compounds have very high conductivities. They're very good conductors of electricity because there's these free electrons that can move around. They also have, as a result, high melting points and boiling points. The other thing we need to know about metallic bonds is how we can form things called alloys. Alloys are, greater than or equal to two metals or two compounds, two elements, that form a metal. So examples of alloys that we're familiar with are bronze, brass, and these are mixtures of different elements that can make metallic bonds stronger, can make them have higher melting points, higher conductivities, and whatnot. And that's a common thing that's practiced in industry. Covalent bonds between nonmetals. Okay? Electrons are shared between those two atoms. So for example, if we have F2, fluorine gas, the way we would draw the Lewis structure, which we'll cover in more detail in a little bit, shows that these two electrons here are being shared between those two fluorine atoms. What we need to know about covalent bonds is their specific names of bonds. A sigma bond is what happens when you have a single bond. If you have a sigma plus a pi bond, that's a double. And if you have a sigma plus 2 pi bonds, you get a triple. And remember, these form based on how orbitals overlap. When orbitals overlap directly, they make sigma bonds. Indirectly, they make pi bonds. We need to know how these are related to each other. Okay? So out of these bond types, single bonds are the longest and the weakest. They're the easiest to break. They take the least amount of energy. Whereas triple bonds are the strongest and the shortest. Obviously, double bonds fall in between the two of those. We also need to know about network covalent bonds. So these are a series of covalent bonds in a huge network, in a pattern. So common examples that we need to know are diamond and quartz, which is, this is a parentheses, diamond and quartz, which is silicon dioxide. as you can see in the diagram below, if we zoom in on the atoms in a diamond, basically each one of these black dots here represents a carbon atom. And we can see that they're all interconnected in this particular pattern. This forms compounds with very high melting points / boiling points, and they're very hard. In fact, diamond is the hardest substance known to man. Since there's no free electrons, these have very low or no conductivities because there's no electrons to flow freely amongst those atoms. So those are the four main types of bonds we need to know. We're going to focus now on compounds that have covalent bonds because that's where a lot of diversity occurs. Polarity is a new term that we learned, which basically means an uneven distribution of charge. Okay? And what effect does this have? Well, for example, the reason molecules can become polar or not, it's based on electronegativities, which I'm going to abbreviate E sub n, or En. So for example, if you have a bond between F2, like we talked about before, the Lewis structure would look like this, fluorine bonded to fluorine. Since these are the same element, they have the same electronegativities, which means they want electrons equally. So think of it as a tug of war. These electrons in this bond are getting pulled this way and this way equally. So this bond would actually be non-polar. It's not unequal. On the other hand, if you had a bond like HF, here we have one element that wants electrons more than another. In that case, it's fluorine because it's more electronegative. So since it wants electrons more, it's going to pull on these two shared electrons a little bit more than the hydrogen will. Since the electrons are closer to fluorine, and fluorine has a negative charge, we would draw a little sigma negative and sigma positive here to indicate the slight charges on those two elements. We could also draw what's called a dipole. HF would have a dipole that would be drawn like this, where the arrow points towards the negative side of the bond. Down here, this is H2O. The Lewis structure for H2O looks like this. What does the red region represent? Well, this reddish region represents slight negative charge, and the blue region represents slight positive charge. How do I know that's true? Well, oxygen is way more electronegative than hydrogen, so it's going to pull electrons towards it from hydrogen. As a result, it's going to have a slight negative charge, and these hydrogens will have a slight positive charge, giving oxygen a dipole in this direction, towards the oxygen. That is called a dipole moment, the arrow. All polar molecules, so this would be polar, and this would be polar, have dipole moments, permanent dipoles. And depending on the amount of dipoles and the charge and the distribution, the polarity, that gives way to different intermolecular forces, IMFs. Remember, intermolecular forces are forces of attraction or bonds between molecules, meaning between two different molecules. So here is one atom of water, H2O, a molecule of water. Here's another molecule of water. This dotted line represents an intermolecular force, a force of attraction. The reason there's a force of attraction here is because we said that water is polar. It's got a dipole in this direction, so the hydrogen is slightly positive, and the oxygen is slightly negative. So since these are oppositely charged, there's some attraction here. And depending on the number of intermolecular forces, that's going to affect certain properties of these molecules. This one is labeled a hydrogen bond. Let's get into more detail about hydrogen bonds. Okay? Hydrogen bonds are the strongest intermolecular force. And they can only form between a hydrogen that's on fluorine, oxygen, or nitrogen, and fluorine, oxygen, or nitrogen. And the reason for this is because these elements are very electronegative. So they pull electrons away from hydrogen, making it slightly positively charged and making these negatively charged. So if a molecule does not have fluorine, oxygen, or nitrogen, it cannot form a hydrogen bond. That gives, since water forms hydrogen bonds, that's what gives water its very high boiling point relative to other molecules of its same structure. So hydrogen bonds are the strongest. We need to know how they form as described here and how to identify them in diagrams. The next strongest are dipole-dipole, sometimes called dip-dips. Okay, just a faster way of saying it. Dipole-dipole forces they're because of polar molecules. So a hydrogen bond is a specific type of dipole-dipole force that's a little bit stronger. Let's look at an example here. HCl. This is a polar molecule. It has a dipole pointing towards the chlorine because chlorine is more electronegative than hydrogen. It has a slight negative charge. So as you can see here, the negative charged chlorines are always next to positively charged hydrogens. Opposite charges attract, so every single one of these is a dipole-dipole force. A dipole-dipole intermolecular force between all of these molecules of HCl. The third intermolecular force that we talked about that we need to know are called London dispersion forces, LDFs. What we need to know about LDFs is that they are temporary. So they can form even in nonpolar molecules. And they result from the random movements of electrons. So for example, here's an atom of hydrogen. Here's another atom of hydrogen. If this electron moves over here, the electron that's right here is going to be repelled. It's going to push away. So we're going to get a slight negative and a slight positive. That's temporary. That's going to give a slight attraction between these. So if these form in all covalent molecules, so if you need to identify the intermolecular forces, LDFs are in all molecules that are covalent. They are the weakest of the intermolecular forces that we've talked about. So it goes hydrogen bonds, strongest, dipole-dipole, then LDFs. There's two things that affect London dispersion forces. Atom size. So if you increase the size of an atom, and now you need to know your periodic trends. Remember, bottom right corner, biggest atoms. If you increase the size of the atoms, you have more London dispersion forces, or they're stronger. And the vocab word we need to know for that is because you have increased polarizability, which basically means the ability to become polar. The other one we need to know is surface area. And it's the same logic. If you increase surface area, you're going to increase LDFs because you're increasing polarizability. So an example, let's say you had a molecule of like this with these carbons in a long line, 5 carbons in a line with hydrogens branching off. This molecule has more surface area than a molecule that looks like this. Carbon, 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 carbon with hydrogens coming off. So we would expect this molecule to have more London dispersion forces, stronger intermolecular forces. So what's important about that? Who cares? Well, it affects properties of molecules that we need to know. So first one, melting point. That's the temperature at which something melts. Or another way of saying that is going from a solid to a liquid, or back and forth. This is directly related to IMFs, meaning if you have more intermolecular forces, the molecules are held together stronger, so it takes more energy to break them apart when you need to go from a solid to a liquid. So that means you are going to have a higher melting point. Boiling point, it's the temp when you go from a liquid to a gas, or vice versa. And it's the same thing, direct relationship. Stronger IMFs means it's harder to separate the molecules, which means you have a higher boiling point. The last one we need to know is vapor pressure. So this is the pressure above a liquid. So here's a solution, here's the liquid. There's gas molecules floating around. The pressure of that gas, that's the vapor pressure. This is inversely related, or indirect. Okay? So what do I mean by that? If you have stronger intermolecular forces, that means you're going to have a lower vapor pressure. And the reason for that, stronger intermolecular forces, the molecules are held together tighter in the liquid, so it's less likely that they're going to turn into a gas. It's going to take a ton of energy to move them into a gas, so you'll have fewer gas molecules, which leads to a lower pressure. You need to know those three relationships about intermolecular forces. And that is part one of Big Idea.